Acceleration is the time derivative of velocity. So we have a particle moving along some world line x mu of tau. So this world line is parameterized by proper time, tau. All right, and the velocity vector at this point, let's call the velocity u, so that's just another notation for the derivative operator d by d tau. The velocity vector at this point is u of, say, p, that's point p. The velocity vector at this point, u at q, that's point q. And the acceleration then of this world line is obtained by parallel transporting this vector back to p and then subtracting and dividing by the time interval between q and p. So this is acceleration A is the limit of u at point q transported back to point p, then subtract u at point p and divide by the time interval. We know how to compute this. This is just a special case of the derivative of a vector field along some curve x mu of lambda. So let's let this be the vector field v. So this is the point P, the point Q. This is v at point P, v at point Q. Let's call the tangent to this curve t. So that's just another name for d by d lambda, that derivative operator. Then the derivative of this vector field v along this curve, which I've denoted by dv d lambda, is just the limit of v transported from q to p minus v at point p divided by delta lambda. And we know how to compute this. This is, if we look at the muth component of this vector, it's just given by the covariant derivative in the direction defined by the tangent vector of v. In the case of acceleration, we're differentiating the vector field u along the direction defined by the tangent vector u. So what we've denoted by t and v here are actually both the same vector field u for acceleration. So what we find is that the muth component of the acceleration is u alpha del alpha u mu. And of course the acceleration vector itself is the derivative operator a mu d by dx mu. Let's expand the components of the acceleration in terms of ordinary derivatives and Christoffel symbols. This is u alpha partial alpha u mu plus gamma alpha beta mu u beta. But remember, u alpha, the components of the four velocity, is just partial x alpha with respect to tau. So we can write this as, first looking at this first term here, this is partial x alpha with respect to tau times partial alpha, that's actually partial with respect to x alpha of u mu, which is partial x mu with respect to tau. So that's the first term, and the second term here is, let's write the Christoffel symbols first, gamma alpha beta mu times u alpha u beta. So that's partial x alpha with respect to tau, partial x beta with respect to tau. All right, notice by the chain rule, this combination is just d by d tau. So we have d by d tau acting on d by d tau of x mu. So this gives the second derivative of x mu with respect to tau squared plus gamma alpha beta mu partial x alpha with respect to tau partial x beta with respect to tau. These are the components of the acceleration vector. Now you might notice that this first term is what you might have guessed would be the acceleration vector, the second derivative of x with respect to time, in this relativistic context, proper time. So you might think of this as the, say, the naive definition of acceleration. Naive, but incorrect, right? Of course, if we're working in special relativity, that's flat space-time with Minkowski coordinates, then the metric is just constants, and the Christoffel symbols all vanish. So this would be the correct definition, this term alone, in special relativity. But in a general curved space-time, this is the correct definition, including the Christoffel symbol terms. Let's work through an example. Let's consider two-dimensional flat space-time. Let's use Rindler coordinates. Now, previously when I've used Rindler coordinates, I've used the coordinate names rho and tau. So the line element looks like minus rho squared d tau squared plus d rho squared. But I don't really like this choice because this coordinate tau might be confused for proper time along the world line. So let me change the coordinate names, and instead of rho and tau, let me just go ahead and use x and t. So the line element is minus x squared dt squared plus dx squared. And let's take a world line. Let's take a simple one. Let's say t of lambda is lambda, and x of lambda is just a constant. Pick any number, let's say 3. So in terms of these coordinates, this is the x, t plot. This world line is just a constant in x. The first thing we need to do is re-express the world line in terms of proper time. So let's compute d tau squared is minus ds squared, so that's x squared dt squared minus dx squared. X is 3, so x squared is 9. dt is d lambda, so that's d lambda squared, and dx is 0. So this is just 9 d lambda squared, which tells us that d tau is equal to 3 d lambda. And we can integrate that to find tau is equal to 3 lambda. Of course, when we integrate, there's an arbitrary constant here, but that just shifts where the 0 reading of the proper time clock is. So we can just let that constant drop, let it be 0. All right, so the world line in terms of proper time is t of tau equals tau over 3, and x of tau is just the constant 3. So now our acceleration is second derivative of the coordinates with respect to tau squared plus gamma, alpha, beta, mu times first derivatives. Let's remind ourselves that the Christoffel symbols can be written in terms of derivatives of the metric as 1/2 g upper mu nu, that's the inverse metric, times partial alpha g beta nu plus partial beta g alpha nu minus partial nu g alpha beta. So we could proceed to calculate all of these Christoffel symbols, but in this simple example we don't really need all of them. So let's hold off on that. Notice that for this world line, partial x alpha with respect to tau, the first component is just derivative of t with respect to tau is 1/3. And the second component is just 0. It's the derivative of constant. So only when the index alpha is equal to t do we have something non-zero in these terms. And also if we differentiate this again with respect to tau, we just get 0. So in fact, all of these terms are 0. So using that information, we have the components of the acceleration is gamma, mu, and now in this sum over alpha, the only terms that are non-zero are the terms in which alpha is equal to t. And similarly for beta, in the sum over beta, beta has to be t, or else dx d tau is 0. So this is gamma mu tt times partial t with respect to tau, partial t with respect to tau. So that's gamma mu tt times 1/3 squared, which is 1/9. All right, so we really only need these Christoffel symbols. So to compute these, we're going to need the metric and the inverse metric. Let's remind ourselves the metric is minus x squared 0, 0, 1. And the inverse metric, then it's easy, it's just the inverse of these diagonal entries, minus 1 over x squared 0, 0, 1. So we'll start with gamma t, inserting mu equal t, alpha equal t, and beta equal t into this expression. We have 1/2 gt nu partial t gt nu plus partial t gt nu minus partial nu gtt. All right, there's a sum over this repeated index nu, but since the inverse metric is diagonal, all of those terms in the sum will be 0 unless nu is equal to t. So we can set nu equal to t in all of these terms. And now notice each of these terms has a derivative with respect to t, but none of the metric components depend on t. So this is equal to 0. All right, so now let's look at gamma xtt. That's 1/2 gx nu partial t gt nu plus partial t gt nu minus partial nu gtt. All right, now same reasoning. Because the inverse metric is diagonal, this index nu has to be an x. So we can put x in place of nu in all of these terms. And these terms vanish again because none of the metric components depend on t. But this term is a derivative of, with respect to x, of gtt. So it's a derivative of this component with respect to x, and that's non-zero. Right, so this is 1/2 g upper xx, that's 1, times minus partial x of gtt. Well, that's minus 1/2 partial x of minus x squared. All right, so the result is that's minus 2x. The minus 2 cancels the minus 1/2. This is just equal to x. So the components of the acceleration, which we have written here, 1/9 gamma mu tt, so since gamma ttt is 0, that means the t component of acceleration is 0, and for the x component we have 1/9 times gamma xtt, which was x, but along the world line, this should be evaluated along the world line, x is equal to 3, so this is 1/3. Right, so the acceleration vector is 1/3 d by dx. Let's compute the magnitude of A, denoted this way. All right, so the square of the magnitude is just the inner product of A with itself. So in terms of components, that's A mu, G mu nu, A nu. And we know the components of A are 0 and 1/3. So that's 0, 1/3. The components of the metric are minus x squared, but along the world line, that's x is 3, so minus x squared is minus 9. And again, A nu is 0 and 1/3. All right, so carrying out this calculation, we have minus 9 times 0 plus 0 times 1/3 is 0. And the second entry is 0 times 0 plus 1 times 1/3. This is 0 plus 1/9 is 1/9. So the magnitude of the acceleration is 1/3. What this means is if you're in a rocket ship traveling along this world line, what you'll find is that your acceleration is 1/3 in whatever units you're using, meters per second squared or kilometers per hour squared or whatever. And the direction of the acceleration is given by, it's in the direction of this vector, d by dx. Now one thing you should notice, let me write down once again the components of the acceleration vector in this example were 0 and 1/3. And the world line was given by t of tau equals tau over 3, x of tau equals 3. So that tells us that the components of the velocity are dt by d tau is 1/3, dx by d tau is 0. So you'll notice that in this example, the acceleration vector and the velocity vector are orthogonal. So explicitly, if we compute the inner product of u and a, so in terms of components, that's u mu, g mu nu, a nu, this is equal to 1/3, comma 0. The metric along the world line is -9, 0, 0, 1, and then a is 0, 1/3. So this, if you work it out, is 0. Now this isn't just an accident of this particular example. It's always true that u and a are orthogonal. Orthogonal in the sense that they have 0 inner product with each other. We can prove this by computing the inner product in general for any world line. That's again u mu, g mu nu, a nu. Now in doing and I'll do the calculation in a moment, but first let me point out that we're going to need to use an identity that you probably have already noticed or you might remember from special relativity, and that is the fact that the inner product of the velocity with itself is always equal to -1. Okay, and we can prove this by simply writing out what is the inner product of u with itself. In terms of components, it's u mu, g mu nu, u nu, but the components of the velocity are derivatives of x with respect to tau. And now you'll notice if I gather these terms in the numerator together, and if you'll allow me a slight abuse of notation here and write this as dx mu and dx nu, and then d tau squared in the denominator, then you'll notice what the numerator is just ds squared or minus d tau squared. So that's minus d tau squared divided by d tau squared is -1. So the inner product of any 4 velocity vector with itself is always -1. So we'll use that in computing this quantity. We have the inner product of u and a, that's u mu, g mu nu, a nu. And before I go on, let me use the following notation. Remember, this is a covector, and it's the covector obtained by letting the metric act on the vector u. And we usually denote that covector, the components of that covector, as u with a lower index. Okay, u nu. We refer to this process as lowering the index. Right, so this is u nu, a nu. And now using the definition of the acceleration, we have u nu, u alpha del alpha u nu. So let me write that as, let me just reverse the order of a couple of these terms. We have u alpha u nu del alpha u upper nu. And now let's write this as del alpha acting on u nu minus del alpha acting on u lower nu. Right, so what I've done here is I've used the product rule of covariant differentiation. So you notice here we have two terms, one in which del acts on the u with the upper index, and that just gives this term here. The other term that we get from using the product rule, this del acts on u with the lower index, and it gives a term that's precisely this term that's being subtracted away. So you can see that this is indeed an equality. And now we'll use our result up here, that the inner product of u with itself is always minus 1. Okay, this is the inner product of u with itself. We can write this, if you like, as u mu, g mu nu, u nu, by reversing the lowering of the index. So this is minus 1. So this is the derivative acting on a function minus 1, and the covariant derivative acting on a function is just the ordinary derivative. So ordinary derivative of minus 1 is 0. So this term is 0. So now we're left with this term. We have minus u alpha del alpha acting on u nu, and now let me go ahead and undo that lowering of the index and write u lower nu as g nu mu, u upper mu. And then we have times this u nu. All right, now I'm going to use this another, well, let me first of all use the product rule to separate these terms with this covariant derivative first acting on g, and then the covariant derivative acting on u upper mu. Now I'll use another very important identity. This is equal to 0. All right, I gave this as one of the practice problems in a previous lecture, but it's always the case that the covariant derivative of the metric itself is 0. And you can prove that by just expanding this out into ordinary derivatives and Christoffel symbols, and then using the expression for the Christoffel symbols in terms of derivatives of the metric. So what you have here is a long expression involving lots of derivatives of g mu nu, and term by term they'll all cancel to give you 0. So this is an important result that we'll use over and over again in this course. All right, so with this term equal to 0, we're just left with this term. And if you like, we can also use this metric here that's wired together with these velocity components here to lower the index. So this is minus u alpha u mu, that's this u nu with the index lowered, del alpha u mu. Okay, this is equal to, if we pull out the u minus u mu, what we're left with is u alpha del alpha u mu, but that's just the acceleration. Okay, so if you'll notice, what I've proved is that u inner product with A is equal to minus u inner product with A. So the only way something can be equal to minus itself is if that something is 0. All right, so indeed, the forward velocity and the acceleration are always orthogonal. To understand the physical meaning of this orthogonality relation, I'd like to revisit some of the things that we've learned about special relativity. So that's just flat space-time. And we'll consider the two-dimensional case with Minkowski coordinates. T and x, so the line element is minus dt squared plus dx squared. So here's the space-time diagram, x and t. Let's say we have an observer traveling along some world line like this. Now at some given instant, say right here, we know that, let's say that the slope of this world line at this point, so I'll draw a little tangent line. The slope is, say, dx dt equals v. Well, we know that for this observer at that instant, the set of events that observer sees as being simultaneous with this event are a set of events that look something like this. They have slope dx dt equals 1 over v. So these are the simultaneous events, simultaneous with one another. So let's look at this, the world line, dx dt. What is the forward velocity of such a world line? Well, remember the forward velocity is partial x mu with respect to tau. So that's the two components are partial t with respect to tau and partial x with respect to tau. But this is telling us that partial x with respect to tau is equal to v times partial t with respect to tau. So we can write this as partial t with respect to tau, comma, v partial t with respect to tau. This factor is actually the relativistic gamma factor, gamma, which is defined to be 1 over the square root of 1 minus v squared. And so our forward velocity for this observer at that point is gamma, comma, gamma v. And you can check, one way that you can prove to yourself that this factor is equal to gamma is to check that u is normalized. In other words, u mu, g mu nu, u nu is equal to minus 1. So check this. All right, so that's the velocity of this observer at that point. Now, what about this set of events? This set of events tells us that if we parameterize the points along this curve by some parameter lambda, this is telling us that dx d lambda is 1 over v dt d lambda. So we can construct a vector, say, call it w, that points along the direction of the simultaneous events. So that's the vector d by d lambda. And its components would be partial t with respect to lambda, partial x with respect to lambda. But we now know that dx d lambda is 1 over v. So let me pull out the dt d lambda, 1 comma 1 over v. And so, well, depending on how we choose the parameter lambda, we have different vectors of different lengths, but they all point along this direction of simultaneous events. So this is the vector w. And of course, the velocity vector, u, points along this way. All right, so we might as well just choose lambda to be t and drop this factor. All right, so our vector w has components 1, 1 over v. So this points along the direction of the events that the observer sees as simultaneous. And now what I want you to notice is that these two vectors, the velocity vector and this vector of simultaneous events, they're orthogonal. Okay, so in other words, u mu, g mu nu, w nu, let's just compute it. U is gamma comma gamma v. The metric is -1, 0, 0, 1. And w is 1, 1 over v. So this is gamma, gamma v, -1 times 1 is -1, 1 times 1 over v. We have minus gamma plus gamma v times 1 over gamma. I'm sorry, 1 over v. So the v's cancel, minus gamma plus gamma is 0. So indeed, u and v are orthogonal. All right, so the meaning of a vector that's orthogonal to the velocity of an observer is that vector points along the set of events that that observer sees as being simultaneous. So now we can understand how to interpret this orthogonality between the velocity and acceleration. It's telling us that for the observer who's traveling along the world line with velocity u, the acceleration points along the direction of simultaneous events. So in other words, for that observer, A is a purely spatial vector. So if you've wondered what it means to have acceleration with 4 components, when we're used to thinking of acceleration as just being a 3-component object, well, in a sense it is just 3 components because it's a purely spatial vector. Now, you might be worried that my explanation is not really valid because I use special relativity to argue that vectors that are orthogonal to the velocity lie along the surfaces that the observer views as being simultaneous, and in that sense, the spatial directions. All right, but in fact, the argument based on special relativity is okay because of what's referred to as the principle of equivalence, and we'll talk about this more later. The principle of equivalence basically says that the physics locally, for any observer, it's just the same physics as what we have in special relativity. Or to say it geometrically, the geometry in any local region looks flat. It looks like the geometry of special relativity. So these notions of orthogonality and simultaneity actually carry over from special relativity since they're just local notions defined at point by point at each point in the space-time. We previously defined a Timelike geodesic to be an unaccelerated world line. So this is the world line that would be followed by a particle or observer in free fall. Free fall meaning there's no external forces acting. And we previously defined Timelike geodesics as curves that extremize proper time. So now let's prove that the curves of extremal proper time are unaccelerated world lines. You start with the line element, written in general as g mu nu dx mu dx nu. Now I'm not writing an outer product symbol here because I'm just thinking of these as delta x's, small changes in x. So this is minus d tau squared. So d tau itself is square root of minus g mu nu dx mu dx nu. And now for a world line, x mu of lambda, so it's parameterized by some parameter lambda, we can let x mu dot be shorthand notation for partial with respect to lambda. And now d tau is the square root of minus g mu nu x dot nu d lambda. We can integrate this to find the proper time between two events, say event at lambda 1 and the final event at lambda 2. Integral d lambda of square root of minus g mu nu x dot nu. So we want to extremize this, and we know how to do that from Lagrangian mechanics. We simply vary the proper time with respect to the world line functions x mu of lambda. So that's delta tau equals the integral from lambda 1 to lambda 2 of d lambda. The derivative of the square root is 1 over 2 times the square root. That's square root of minus g mu nu x dot nu. And now we differentiate what's under the square root. We have minus g mu nu x dot mu delta x dot nu minus g mu nu delta x dot mu times x dot nu. And let's remember that the metric components can depend on the x's, so this is also minus partial with respect to x alpha of g mu nu delta x alpha, and we also have then x dot mu x dot nu. All right, before I go on, let me point out there's a slight abuse of notation here. I've used the Greek letters mu and nu for the indices in this term, in this square root, and I've also used mu and nu in terms like this. And of course, these are repeated indices. For example, mu is repeated here, so there's a sum in this term. There's also a sum in this term, but these are separate sums. So there's actually a double sum here over mu and nu under the square root, and another double sum out here. So strictly speaking, I should probably change these indices to something else. But I think in this context, there's really no confusion that there's not just a single sum over all of these terms. It's really a double sum under the square root and another double sum out here. So I'll just leave this as it is. Now look closely at this term. Right, we can write this term as g nu mu x dot mu delta x dot nu, just because we know that the g's are symmetric in their indices. But these indices mu and nu are being summed over, so we can call them anything we like. So in particular, we can let nu equal mu, and we can let mu equal nu. So we can write this as g mu nu x dot nu delta x dot mu. So written this way, you see explicitly that this term is equal to this term. So we have really two of these terms. So let's write delta tau then as integral from lambda 1 to lambda 2 d lambda 1 over 2 times the square root, and I won't even bother to fill in the argument of the square root. This is minus 2 g mu nu x dot nu delta x dot mu from these two terms, and then this last term is partial alpha g mu nu x dot nu delta x alpha. All right, the next step is to integrate by parts to remove the dot from this delta x. So we have integral from lambda 1 to lambda 2 of d lambda. In this first term, we have a 2 that cancels the 2. There will also be a minus sign from the integration by parts that cancels this minus sign. So what we're left with is the dot, or d by d lambda, of g mu nu x dot nu divided by the square root. And all of that is times delta x mu. And the remaining terms here are minus partial alpha g mu nu x dot mu x dot nu. We have the 2 square root in the denominator and then delta x alpha. Now you'll notice both of these terms have a factor of delta x, but the indices don't line up. Here we have a mu, here we have alpha. And I'd like to pull these factors out as a common factor, but I need to make sure the indices line up first. So Let's just look at the denominator here, including the delta x alpha. We can write that by shuffling the indices around. Remember, these are repeated indices, so I can call them anything that I like. So instead of alpha here and here, we'll use mu. So we'll have partial mu of g, and then we'll have a delta x mu. And then for these indices, I need to change the mu here so it's not confused with this mu. So we'll call these indices alpha and beta. So this is g alpha beta, x dot alpha, x dot beta. So writing this term in this way, then the variation of the proper time is integral from lambda 1 to lambda 2 of d lambda, partial with respect to lambda of g mu nu x dot nu over the square root, minus partial mu g alpha beta x dot alpha x dot beta over 2 times the square root, and all of that is times delta x mu. Remember, we want to extremize the proper time, so let's set delta tau equal to 0, and now apply the usual reasoning. For delta tau to be 0 for arbitrary delta x mu, then the coefficient of delta x mu must vanish. So that gives us the equation 0 equals partial with respect to lambda of g mu nu x dot nu over the square root minus 1/2 partial mu g alpha beta x dot alpha x dot beta over the square root. So this equation describes timelike geodesics for an arbitrary parameter lambda, but in particular it holds if that parameter lambda happens to be equal to proper time. As a particular case. So we can set lambda equal to proper time here, and the equation will still hold. And if you recall what the square root is, the square root, under the square root, we had minus g mu nu x dot mu x dot nu. So if lambda is proper time, then x dot is just the velocity. So this is the inner product of the velocity with itself, which is always equal to minus 1. So we have minus minus 1, which is 1. So the square roots here and here go away because they're the square roots of 1. So writing this equation in terms of proper time, we have partial with respect to tau of g mu nu x dot nu, and now let's be careful here, the dot now refers to d by d tau, not d by d lambda. Okay, and the remaining terms here are minus 1/2 partial mu g alpha beta x dot alpha x dot beta. So we can simplify this by using the product rule. This is g mu nu x double dot nu plus the derivative acting on g mu nu by the chain rule, that's partial alpha g mu nu x dot alpha times x dot nu minus 1/2 partial mu g alpha beta x dot alpha x dot beta. So now let's multiply through by the inverse metric. So we'll multiply this equation by g upper sigma mu. And what we have is that g upper sigma mu, g lower mu nu, x double dot nu, plus g upper sigma mu times partial alpha g mu nu, x dot alpha x dot nu, minus 1/2 partial mu g alpha beta x dot alpha x dot beta. All right, this combination is just the Kronecker delta sigma nu, and we have a sum over nu, and in that sum the only term that survives is the term in which nu is equal to sigma. So this is x double dot sigma. Now in these terms, notice we have two factors of x dot. I'd like to pull those out as common factors, but the indices don't line up. So let's, here we have x dot alpha and x dot beta. If we can just convert this nu to a beta, then these factors will have the same indices. So let's replace nu here and here with beta. So we have then g upper sigma mu partial alpha g beta mu, or actually g mu beta, but I can reverse the order of those indices if I like, because g is symmetric, minus 1/2 partial mu g alpha beta times x dot alpha x dot beta. And now notice that since this is a symmetric combination, symmetric between alpha and beta, I can reverse alpha and beta if I like, which means I could, if I wanted to, write this term as partial beta g alpha mu. It would be the same thing when we sum over alpha and beta multiplied by these factors. So we can also split the difference and write half this term plus half that term. So this is equal to x double dot sigma plus g sigma mu times 1/2 partial alpha g beta mu plus 1/2 partial beta g alpha mu minus 1/2 partial mu g alpha beta, and all of that is times x dot alpha x dot beta. Now this should start to look familiar. Let's just pull out the factors of 1/2. This is 1/2 g sigma mu partial alpha g beta mu plus partial beta g alpha mu minus partial mu g alpha beta times x dot alpha x dot beta. So this, of course, is just the Christoffel symbols: gamma, alpha, beta, sigma. All right, so our geodesic equation, written in terms of proper time as a parameter, is 0 equals x double dot sigma plus gamma sigma alpha beta x dot alpha x dot beta. And just remember, the dot is a derivative with respect to proper time, so we can write this more explicitly as the second derivative of x sigma with respect to tau squared plus gamma sigma alpha beta partial x alpha with respect to tau partial x beta with respect to tau. So this is the geodesic equation. And of course, you'll notice the right-hand side is precisely the components of the acceleration vector. So this is A sigma, components of acceleration. And let me remind you that we defined the components of the acceleration vector as forward velocity u alpha, del alpha, u sigma. And then we showed that that's precisely the right-hand side here when written in terms of the world line x of tau. So what we've shown is that the geodesics, and this is for Timelike geodesics, the geodesic equation is just the equation acceleration equals 0. So Timelike geodesics are world lines with acceleration equal to 0, unaccelerated world lines. So this is referred to as the geodesic equation. Let me write it once again. This is 0 equals x double dot mu plus gamma mu alpha beta x dot alpha x dot beta, where x is a function of proper time, so the dot here refers to differentiation with respect to proper time. So this is the geodesic equation. And we also know that it just is the statement that the acceleration is equal to 0. So the way we obtain this from a variational principle is we consider two events, say an event here and an event here, two events that are time-like related to one another. In other words, this event is within the region of future light rays emanating from this event. So in other words, these two events can be causally related to one another. And for such events, we can have, of course, lots of world lines that connect those events, but the geodesic is the one that extremizes the proper time between those events. So this type of geodesic is referred to as a time-like geodesic. Now what happens if we pick our 2 points like this? So this point is not inside the future causal region or the future light cone of this event. These events are space-like related. Well, we can connect those events with curves of a certain proper distance that we could compute using the line element. And then we could extremize that proper distance s. And we can imagine doing that calculation. It's basically the same calculation as the one that we did for time-like geodesics. And what we would find is a space-like geodesic. That satisfies an equation that looks just like this one. So x double dot mu plus gamma mu alpha beta x dot alpha x dot beta. Only in this case, the dot refers to proper distance. So this is gives us a space-like geodesic. And the space-like geodesic would be parameterized by proper distance, whereas the time-like geodesic would be parameterized by proper time. Now, what about the case in which these two events are light-like related, or null? All right, so we have two events here, and they can be connected by a light ray. What path does a light ray take in going from here to here? Well, in this case, it's a little bit more tricky to define, because recall that the line element, ds squared, is g mu nu dx mu dx nu, and that's also minus d tau squared. So in the case of time-like geodesics, we parameterize our curves with proper time tau. In the case of space-like geodesics, we parameterize with proper distance s. But in this null case, the light-like case, ds squared is 0, or d tau squared is 0. They're both 0, so there is no ds or d tau. But we can still parameterize the curve between events with some parameter lambda. So we'll call this curve x mu of lambda. And we can apply the same reasoning we did in the time-like case. For a time-like geodesic, so if this is the velocity at one point, say P, here's the velocity at a later event Q, what we for a geodesic, we demand that the parallel transported Q back to P coincides with the vector that's already at P. That's the condition that U alpha del alpha U mu equals 0. Okay, so we can do the same thing here. We can introduce the tangent vector, let's call it T, as d by d lambda. So here's the tangent vector at one point, here's the tangent vector at another point, and we can demand that when we parallel transport this vector back to this point, say from point Q to point P, that the two vectors, well, they don't actually have to coincide with each other, but it's enough that the vectors be pointing in the same direction. Because after all, this parameter lambda is arbitrary, which means we can place the tick marks sort of arbitrarily far apart or close together along the world line, and so that will affect the length of these vectors at various points. So really all we need to demand is that when we parallel transport this vector from Q that's the vector d by d lambda when we transport it from q back to p, that they lie in the same direction. So the condition for that is that T alpha del alpha T mu should be proportional to T mu. So a null geodesic, or the path of a light ray, is one that satisfies this condition where T, the components of T, are just the derivatives of x with respect to lambda. You can imagine, though, that if we had just the right parameter, we could arrange those tick marks to be just the right distance apart so that when we did parallel transport this vector q back to p, that it would coincide exactly, not just to within a overall multiplicative factor. So it turns out that for the right choice of parameter lambda, you can arrange for this proportionality to be 0. So such a parameter lambda is called an affine parameter. So for an affine parameter, the equation that describes null rays or light rays is T alpha del alpha T mu equals 0. Or in terms of components, it's just the equation x mu double dot plus gamma mu alpha beta x dot alpha x dot beta. So again, this is the geodesic equation, but in this case, the dot is d by d lambda, and this is a set of differential equations for the curve x mu of lambda. So from a mathematical point of view, we just have one equation. It's the geodesic equation. X double dot mu plus gamma mu alpha beta x dot alpha x dot beta equals 0. And this is a set of differential equations that we can solve, and whether the curve that we get is time-like, space-like, or null really just depends on the boundary conditions or the initial conditions we use in solving these. And if the curve is time-like, then we refer to the parameter as proper time. If the curve is space-like, the parameter is proper distance. And if the curve is null, then the parameter is an affine parameter. And we can tell whether the curve is time-like, space-like, or null by examining the inner product of x dot with itself, x dot mu, g mu nu, x dot nu, right? In the time-like case, this is just dx mu, g mu nu, dx nu over d tau squared. But the numerator is minus d tau squared, so this is minus 1. So this is the case for a time-like geodesic. For a space-like geodesic, we have dx mu, g mu nu, dx nu over ds squared. Numerator is ds squared, so this is equal to plus 1. That's the space-like case. And for the null case, this is dx mu, g mu nu, dx nu over d lambda squared, where lambda is the affine parameter. And this is, since the numerator is 0, this is just 0 for the null or light case.